Converting, we remember that there are 1,000 grams in 1 kilogram, and the 1,000 has the decimal at the end. So to turn this 1,000 grams into a single 1 kilogram, what we do is we have to move the decimal point over 1, 2, 3 places, and then the decimal point is right after the 1, like it is in the kilograms. So in our problem here, we are going to move our decimal point over in the same way, 3 places to the left. So it's going 1, 2, 3. Put in the placeholder zeros. So we end up with 0.00723. For converting centimeters to meters, we remember that there are 100 centimeters in 1 meter. The 100 has a decimal point right there. To turn 100 centimeters into a single 1 for the meter, I have to move the decimal point over 2 places to the left. So I'm going to do the same thing over here with the decimal point of the problem. 1, 2 places, and I'll put in the placeholder 0. So 0.0723. On a graph, where do the independent variables usually go? The x-axis. Where do the dependent variables, or what are the dependent variables? These are the qualities that change due to the actions of the researcher. On a graph, where do the dependent variables usually go? The y-axis. A researcher decides to study the age of people and their weight. He chose people with ages 3, 5, 7, and 9. Their weights turned out to be 30, 42, 82, and 90 pounds. Make a graph with this data. Okay, so the researcher could have chosen any person in the entire world with any age whatsoever. The researcher chose the ages of 3, 5, 7, and 9. Could have been other things, but they chose those numbers. And so that means that the age goes on the x-axis. Those are the independent variables. So that means the weight then goes on the y-axis. The weight of the people involved in the research depends upon how old they are. And so that's why we say the weight is the dependent variable. The researcher was free to choose any kind of age that the researcher wanted. We think of freedom and independence, you know, the American way, yay. Okay, so independent and free kind of go together. So the researcher was free to choose whichever age that was independent of anything else. Okay, moving on now. Next, we need to have numbers. So let's see here. We have ages up to 9. So if I just do 1 year per line, that's going to fit just fine. And so we put the label of age, and we should also put the unit. This is not measured in months or days, but these numbers represent years. The weight is going to be measured in pounds, and we'll put in the numbers for that. See, we have up to 90. So if I go by tens, I should be able to cover everything in this graph. Almost. Now, the dots. Let's see here. I'm going to redo this so that the 90 really does line up on one of the lines. So that means I have to start off with the bottom line being 10, and that's okay. You don't have to start off with 0. Okay, that does my heart better. Okay, 3 goes with 30 pounds. A 3-year-old had 30 pounds. A 5-year-old was 42. A 7-year-old was 82. And the 9-year-old was 90 pounds. Okay, there's my graph. Two people are stating their opposition to the theory of climate change. Which is stating a valid scientific argument and which is using a red herring? Go ahead and read those on your own. The one that is based on data and the data that's pertinent to the issue is going to be letter B. This is a good scientific argument. You're looking at whether or not predictions came out to be true, the measurements that we expected, did they come true or not? Is the new data what the predicted data says it should be? Okay, letter A though, that is a red herring because whether or not Mr. Gore uses airplanes does not make the data that he presents as being good, valid data or not. And so that is why that's a red herring. Some people get very upset when they see other people being hypocrites. And so that is a very emotional issue, and that would be an extra reason to call this a red herring. Number 8, start with this equation and derive an equation that has t by itself. So we just want to get the VI and the A away from there. So what I'm going to do is subtract off VI from both sides. And I'll get VF minus VI is equal to AT. And then I want to divide both sides by A. And do I want the T on a certain side? Nope. It does not say to have the T on a certain side at all, so I can have it at any side I want. So we have VF minus VI divided by A is equal to T. And there's our final answer. Take a moment to read the main ideas from the last lesson. You can pause the video to read that. And again, pause the video to read the purpose, relevance, success, grades, and next quiz. There is a video for the STAIR lab so that you can take your own measurements. Be sure you have a stopwatch ready when you play that video. Read the directions and take the measurements from the video and put them into the correct blanks. Please note that in the video I started off with the highest height first, and I worked my way down the stairs to lower and lower heights. And so we're going to be recording our data in the opposite order than what's listed here. For task number 2, what you'll need to do is to replay the video for the STAIR lab. And this time, look at the first drop that I do from the 5-meter mark. And you're going to have to watch that again and do a different measurement. In the first part, the first test, you measured the time for the initial drop from the release down to the floor. For this time, this task 2, you're going to do the timing from the first bounce to the second bounce when it goes in this path here. So that is what you're doing in step number 2. To do this first part, find the velocity of the ball when it's dropped from 5 meters. Let's think about how we're going to be doing that. Let's see here, we have the equation A equals delta V all over T. Would that help us out? Let's double check this. We know the A is negative 9.8. And the change in velocity, well, let's see here. How do we do that? The change in velocity is Vf minus Vi. And the initial velocity is 0, right? Because we're just holding it and then releasing. So that means that in this case, the change in velocity is the exact same thing as the final velocity when it hits the ground. So that's what we're trying to find here, Vf. And then the T here at the bottom, whatever that is, that's going to be the time that we took in the previous part to go from the release down to the first bounce. Okay. So now go ahead and read the rest of this and follow those procedures.